This is Aerodynamics podcast number 34, and today we're talking about Stereo PIV. So PIV, most people have heard about it, and we'll talk about a little bit what that is. But then there's also another technique called Stereo PIV, and it has a significant advantage over regular PIV. And to do that, we're going to look at a paper called Application of Stereo PIV to the 70-degree delta wing at subsonic speed, because they use Stereo PIV here, and they also use Stereo PIV in a validation process, so they want to actually develop their own. So this is good they go through the different components of it. So first of all, what is PIV? In aerodynamics, PIV stands for particle image velocimetry. And what this is you determine what the velocities of the flow is through using lasers and cameras and seeding particles. So what you do is you dump a bunch of seeding particles into the flow. Ideally, these particles will follow the flow well, so that you call that faithfully. That means that when you have even high rotation areas, these particles will still follow that. And that depends on the particle size and density and that. So I'm not going to go into that. That's just a regular PIV. Then these particles are going through the flow, and then you shine a sheet actually through the flow at whatever position you want to determine what the velocities are. So let's say you have an object, a ball, and then just behind it you'll put a laser sheet, and you want it to be very thin. The reason why is because the thicker the laser sheet is, the more corrupt your velocities will be. The reason why is because with PIV, regular PIV, you look at the two velocity components. If you have a thick laser sheet, the particles can then move in the third component, and you'll still pick that up. So you get a bit of corruption through that way. So you want it to be very thin, like ideally a millimeter or two. Now that depends on camera shutter speeds and all that, but that's another story. So you have this laser sheet, and you have these particles in there, and these particles are being illuminated by the laser. So usually the laser is going to be green. That's one of the most common ones. And these particles are going to shine back this light, and you can take a picture of these particles because they're illuminated now. And then very quickly afterwards, you take another picture. Between those two pictures, you can now see where these particles have moved. And because you have lots of particles in the flow, you can get a very good idea as to what the flow is doing, where there is vorticity, if there are vortices, flow separation, all different stuff. And PIV can be used in a transient motion fashion. So if you have a very high shutter rate, you can actually get kilohertz resolution. The temporal resolution is really good. So that's regular PIV. But as I mentioned, you do have the problem sometimes of getting corruption in the velocities. And that's because of the third component. Regular PIV just looks at two components, but you do get that third component which does corrupt the results. Stereo PIV is designed to get rid of that problem. So this paper looks into that. And to do so, they looked at a delta wing, and they said that the angles of attack were from 0 to 45 degrees, and they were investigated with free stream velocities from 20 meters per second to 60 meters per second. So let's talk about PIV now, even more. So they say in this paper, in the past few decades, many countries have set up projects to study the vortex structures and formations of delta wings. And they usually do this through pressure-sensitive paint. And this is also another really cool technique. We're sort of living in almost a golden age for aerodynamics, where we have really cool techniques. We have pressure-sensitive paint, we have PIV, tomography, lots of other things. So pressure-sensitive paint is exactly what it sounds like. It's paint where you just paint on a surface. Then depending on what the pressure is on this surface, the paint will change color. And you obviously need to take pictures of it so you can analyze it later, and you run it through software to get accurate results. But that's really cool. And PIV is also another cool technique. So they're going on and saying particle image velocimetry and other advanced experimental methods measure the surface flow field and spatial flow field of the experimental data. And then that can be used to validate your CFD, because a lot of people want to use CFD these days. Pressure-sensitive paint, as useful as it is, only gets information on the surface of the object. PIV gets information in the wake. They go on and say, using PIV technology to obtain velocity field information and then analyzing the surface flow field of the delta wing according to the velocity field, not only can avoid the influence of various test devices on the original flow field around the delta wing, but also it's possible to measure the transient flow field in real time, which further gives you even more information to validate your CFD. So let's talk about the influence of various test devices. So there are two main categories of experimental methods. There is ones where you stick them in the flow, and then ones where you don't have them in the flow. So for example, if you were to put a hot wire into the flow, that's called intrusive, and that's because you put it into the flow, and it's going to be affecting the flow to some extent. Depending on what application you're looking at, it will be more or less. For example, boundary layers. If you don't do a hot wire properly, it can dramatically affect a boundary layer, and it will really corrupt your results. So they do have different types of hot wires to get around that. But again, it's far better just to use something which doesn't affect the boundary layer at all, and that's something called non-intrusive. Something like pressure-sensitive paint and PIV, in theory, should be non-intrusive. Pressure-sensitive paint, if you don't do it right, can affect the surface roughness, which then does affect the flow. So you can kind of think of that as intrusive because it does affect the flow. PIV, if you don't, again, do it correctly, if you stick the cameras in the flow, for example, that's going to affect the flow. If you have these particles in the flow, they don't follow the flow faithfully, or they even affect the flow, then that's obviously not good either, and that's going to be, again, intrusive. But by nature, they shouldn't be intrusive, these techniques, but if you do them poorly, then they do become so. But the benefits of these are that they do have a lot of power if you do them properly. And they go on and they talk about regular PIV. So the initial development of PIV technology is mainly two-dimensional particle image velocimetry, so 2D PIV. The basic principle is to add tracer particles to the flow field, and the particle velocity represents the velocity of the fluid at the corresponding position. The laser sheet source is used to illuminate the test plane in the flow field, and the CCD camera simultaneously records the position of the particles in the adjacent two exposures. So the CCD camera is just a particular type of camera. It is very fast acting. You can get an entire picture very quickly and accurately. And these are pretty much the standard in PIV. You can use other cameras, but they can run into problems. So the CCD is pretty much the standard for both performance-wise and price-wise. They go on and say the average displacement of the particles at each point in the query area is obtained by the cross-correlation algorithm. So that's what we were mentioning before, where you have two pictures and you look at where these particles have gone, and then you determine, okay, well, this is what the velocity flow field is. If these particles have moved this distance in this amount of time, then we know what the velocity is. Now, how we do that is we get this regular picture and we divide it into all these tiny little frames, and we call them interrogation windows. Now, these interrogation windows might be a few pixels by a few pixels wide. Usually do it on pixels, not particles, because pixels are more evenly distributed throughout the picture, whereas particles, you can get a lot of particles in one area and not many in others. So we usually do it you can do interrogation windows of 8 by 8 pixels, 16 by 16, 32 by 32, 64 by 64, and so on. These are common ones that we use. So that means that each interrogation window has, let's say, 16 pixels in one direction and 16 pixels in the next direction. That's a square. Then in this interrogation window, there will be a certain number of particles. We then look at this exact same interrogation window from one image to the other, and we look at how all these particles have moved. Then we take the average. So we get the average for that interrogation window. And so that means you have a certain resolution for your PIV data. The closer this camera is to the plane, the better the resolution, and also the smaller the interrogation windows, the better the resolution as well. The problem with this second approach is that you then potentially reduce your accuracy because you only have a few particles to look at. So they then go on to the problem of this 2D PIV system, which is it measures only the in-plane projection of the three-dimensional velocity vector, and there are inevitable errors. That is because, as we mentioned, the third dimension can corrupt the results. If you look at it from an angle, you then look at the third dimension of the velocity is then captured a little bit. So you do get a little bit of error there. Moving on to stereo PIV. For stereo PIV systems, it is necessary to perform motion analysis on the particle images of two consecutive frames of the left and right cameras. Firstly, the particle images at the same time of the left and right cameras are matched and fused to find the corresponding regions. So what this means is you have two cameras set up, and you focus them on the exact same area. And then you take pictures of both of them, and then you want to line up how these pictures look. So you can correct for parallax errors, and you can also correct for different velocities because you're looking at them from different angles. Then they say, then based on the correlation analysis of the particle images corresponding to the different moments of the same camera, the displacement vector image information of the particles on the plane can be obtained. Finally, the vector results are obtained. So the spatial displacement of moving particles is obtained after 3D reconstruction. So stereo PIV overcomes the inherent defects of 2D PIV, and the calculated in-plane stereo velocity fields can be more realistically reflected in the in-plane and out-of-plane flow field structures. So by using stereo PIV, you can then get this third dimension, and you can decouple them. So you don't only have two velocities, and both of those velocities are somewhat erroneous because the third velocity is in those two velocities just due to a parallax error and the different errors of the angles that you're looking at the images from. But also now with the stereo, you do get that third component. You've decoupled all three, and that error is not in there anymore, in any of them. If you do it properly, that is. I have to throw that specifier out because even though we do take it for granted, it's not something that we should be taking for granted because it sometimes does happen. So now they move on and they talk about their setup for their PIV system, their stereo PIV system, and then they look at the validation of it. So this is important as well because now we can understand just how it works. So they say, in this study, the velocity vector fields over a 70-degree swept delta wing are obtained at a series of stations in the chordwise direction using a PIV system. So the 70-degree swept delta wing means that the leading edges are swept at 70 degrees. It's quite sharp, and they're using the PIV system on this. The test cases were selected on the basis of the previous results of pressure-sensitive paint. So they have previous results of this method, and they're going to correlate the two later on, which is quite nice. And they were conducted on the same wind tunnel with the same delta wing. So the experimental model is a 70-degree delta wing with a chord length of 298 millimeters and a span of 216 millimeters. What's more, they have 78 taps arranged in 6 lines on the model surface. So that's quite nice. You can get pressure from there as well. And they have a picture of this delta wing, and it's effectively just a regular isosceles triangle. So the base length is about half the length of the other two sides. And now onto the PIV system, they're talking about some of the nitty-gritty. So the PIV system used in this study consists of a double pulsed ND YAG laser. This is a very common laser, like I would say it makes up like 95% of the PIV systems out there, with a maximum pulse energy of 2 by 500 millijoules at a repetition rate of 15 Hertz. So this is again a pretty standard laser here. The energy is a little bit higher than usual. Like it's getting to the point where you can actually start burning through walls now. And the repetition rate is 15 Hertz, which is a regular one. Like you can get kilohertz, but they are very expensive. And then they use two 12-bit digital CCD cameras with 6,600 by 4,400 pixels, and the PC software to do not only running the entire thing, but also to analyze the results later. So the aerosol generator was used for the seeding of DEHS particles. So these are very common particles again. Effectively, they're for fog. Like if you have ever been to a nightclub or a discotheque, as some Europeans call it, then this is what you're seeing in there. The particles were filled in the tunnel beforehand, and the generator was turned off during the actual experiment, so they weren't continually pumping in more seeding particles. One thing to note about this method is that the seeding particles do fall out of the air after a certain amount of time. The greater the diameter of the seeding particles, the quicker the settling rate. So you want to have very small particle sizes, but the trade-off with that is you don't get as much reflection. So the bigger the actual particle size, the more reflection you'll get, which means that it's easier to do your experiments. Again, this is very detailed stuff, and I'm not going to go into that. If you want to know more, you can always get in touch with us. We've got courses you can do to learn about this. We also do PIV systems, so you can buy one of them and don't have to worry about it. Let's move on. So the surface of the model had 6 rows of these pressure taps, and the PIV analysis, the PIV experiments were used to be validated with this data along with pressure-sensitive paint, and they did another thing as well, which we'll get into in a second. Now on to how long you waited between two images. So the time separations between both laser pulses, and in each laser pulse they're taking images, were 100 microseconds. Sorry. For velocity measurements, such small time delays require precise triggering of the lasers and a precise synchronization of the camera's framing times. So they used the synchronizer, which had a resolution of 50 nanoseconds, so it's really good. So why do we pulse the lasers, and why do we take different images? The reason why we pulse lasers is because usually the camera shutter rates are not nearly as fast as we'd like them to be. The lasers can be triggered faster. So by triggering the laser very quickly, the camera shutter will still be open the entire time plus more, but it's not going to be taking in any light until the laser comes on. So it's just going to be black. And then when the laser comes on, it gets that information, and then the laser goes off. The camera shutter is still open, but then it will shut it after that, and then you get the image. If you keep the laser on longer, the particles will move around, and that means you get smearing of these particles, and it's harder to actually do an analysis on it. So that's why you want a very quick laser, and you want it to be very crisp. And that's why you have these synchronizers and all that. It's pretty high tech. So now they go on to the validation of their stereo system. In order to verify the credibility of our PIV system, their PIV system, not mine, this is their paper, series of fixed speeds given by the empty wind tunnel. The velocity fields in the plane are measured through the stereo PIV system and then compared with a given wind speed. The tests included 4 conditions, 20, 30, 40, and 50 meters per second. And I have figures here showing it, and they're actually really good. So all figures, if you're looking on this on YouTube, which you can watch if you're listening to this on our podcast, you can look at the images on YouTube, or you can also download the paper. It's an open access one, so you can get it in a link in the description. This is figure 5, by the way. And what we're looking at here is the 20, 30, 40, and 50 meters per second graphs, and they're showing the velocity of the wind. It's an empty wind tunnel. And they all look pretty good. There's only one artifact between all of them, and that's in the bottom left-hand corner. The velocity is a bit lower, and that's just common between all of them, so that's probably just the wind tunnel. Although actually no, in one of them in 2 of them they're higher, in one of them they're lower. So that might be due to the turning vanes then. Maybe they're having some sort of separation pattern or something, which is then changing the flow. If you want to learn more about wind tunnels actually and how to do them, look at our previous 2 podcasts, 32 and 33. We covered that quite a bit, so you can learn more there. Yeah, so the rest of the wind tunnel is actually quite nice. The test section, the cross section is well validated. One thing that should be noted is the higher the velocity of the free stream, the more inaccurate PIV becomes. That's because, again, the laser sheet is very thin. The particles are only going to stay in the laser sheet for so long. So that means they're going to fall out, which means that instead of having, let's say, 99% of the particles in the laser sheet for both frames, for both pictures, you might only have 90% or even 80% or 50%, which is really bad. You want to keep as many particles in the laser sheet as possible between the 2 frames. The higher the velocity, the faster the more distance these particles travel in that time between the 2 frames, and then they'll fall out of the laser sheet and you get new ones coming in. But overall, this looks pretty good. Like, they're getting a very nice distribution. It's matching the velocity of the wind tunnel. There are a few discrepancies, but that's probably due to the actual wind tunnel quality more than the actual stereo system. And then they have another cool picture. Figure 7 now shows the velocity profiles across section through the delta wings from 0 degrees to 45-degree angles of attack at wind speed of 60 degrees. And you can see these vortices getting really strong, really big and strong as you increase the angle of attack, which is to be expected. Then at a certain angle of attack, the vortices break down. And this is at a distance from the nose, from the leading edge, of 62.5%. So almost halfway, a little bit over halfway. One thing that's cool on this picture, just let's talk about delta wings for a second because this is quite cool, is that I haven't looked into this too much before, but this picture really shows it. So there are obviously two vortices that form over the leading edges. If you want to look more into that, actually, we have a couple of podcasts on delta wings. You can watch them and listen to them, and you'll learn more about delta wings. But just here, just a quick crash course. Over a delta wing, you get two vortices forming over the leading edges. And in these vortices, the velocity is very low, but these pictures show around the vortices, the velocity is actually really high now. So you have the core, which is very low, and then around the actual core, you have a very high velocity. So I haven't seen that before, and that's quite cool. And then when you break down the vortices, the velocity around these vortices are a bit lower. So that high region of velocity is probably due to these vortices inducing the flow around them. So they go on with some more validation. They say the PIV measurements were repeated 4 times while changing the free stream velocities from 20 to 60 meters per second with an increment of 10 meters per second to check the effect of velocity variation from the formation of the vortex. And again, this is really cool. Like these figures, they show similar developments. Perhaps the vortices get stronger, but again, you have high velocity around the vortices, which I've not seen before. That's cool. They say, in order to verify the stability of the stereo PIV systems, the repeatability tests were performed, and they said that they look very good. They match up very well, which they do. So they ran at 30 degrees at 60 meters per second. You have this figure 8. You have 4 different pictures showing each one of these runs, and they all align very well. So they're all showing pretty much the same thing. One thing that I should note is that with any aerodynamics, there's pretty much always going to be some unsteadiness. Like almost every aerodynamics situation, there's some unsteadiness. That means that when you take 2 different measurements, there's going to be some difference between the 2. Ideally, it should be very little, and that's why we average results often. But there's going to be some minor variations, and that's what we do see here. We do see some minor variations. And that's just probably due to which point in the transient cycle they took the pictures at. So this is very acceptable, these results. And they show that the PIV system was working well. They then have another cool image, so figure 9 now, where they have this delta wing at different velocities from 30 to 60 meters per second. On the surface, the suction surface, they have the pressure-sensitive paint results, so the pressure coefficient results. And then they have on the right side of the delta wing, the PIV results showing the vortex formation and breakdown along the leading edge. And they line up very well. Obviously, a vortex is a low-pressure core, and that's going to induce a low pressure on the surface of the suction surface of the delta wing. And then as it breaks down, this low pressure is going to not be there anymore. It's going to be higher pressure, and that's not good for lift. You want to have as low pressure as possible on the suction side to produce as much lift as possible, because you want to have a graded pressure differential between the pressure and the suction sides of any airfoil to increase the resultant force, the resultant lift. And this PIV shows exactly what we would expect. So before we go any further, I just want to say, check out everything we do at Aerodynamics. Check out the instrumentation we do. We do PIV like this. So if you want to get your own system like this, we do that. We also do traverses. We do an instrument called the Atmosphere Hawk that accurately measures the density in your wind tunnels, so you know what the density is and you don't have those errors creeping into your experimental results or your CFD validation. Because often when you do CFD, you assume the density is one thing, but it's not that when you did your experiments. It can fluctuate a few % easily any day. So you need to keep track of that. Our Atmosphere Hawk gets rid of those errors for you. We also do courses. So we do CFD, experimental like for PIV, so you can learn more PIV, all the very detailed stuff. We also do theoretical, so you can look at those courses. And we also do the International Aerodynamics Conference every year. So that's where aerodynamicists get together and talk about aerodynamics. All the links in the description. So let's move on. So they said that this figure here, figure 9, as we were mentioning with the pressure-sensitive paint and these PIV systems, show the typical velocity flow field along 6 different sections. And it clearly reflected the development of the main vortex separation zone above the delta wing in the direction of the flow. As with the flow field characteristics reflected by the pressure cloud map, so the PSP, pressure-sensitive paint, The delta wing has no vortex braking in the selected direction along the flow direction until 80% of the chord length position. Now, interestingly enough, as the velocity increases, it seems like the breakdown was probably a little bit accelerated, it seems. I don't know, like these figures indicate that at the 80% chord mark, as the velocity increased, there was a bit more of a breakdown. So that's the end of this podcast. Make sure to like, subscribe this, check out other podcasts, check out the instrumentation we do here at Aerodynamics, check out the courses we put on, and check out the Intentional Aerodynamics Conference. I'll see you in the next podcast. Peace out.